Hello, welcome to one more lecture on the fundamentals and biomedical application of quantum science and engineering. We, up to now, are dealing with the fundamentals, and we are exposing to you many situations where quantum mechanics is very important, and then, of course, we're going to many applications. Up to now, we've been seeing what we call the scattering problems, and we restrict ourselves to one dimension. But, you know, the dimension is just easy to generalize if we need. And what is this scattering problem? Well, the scattering problem is the situation where we have this physical system here, and we know that the physical system is represented by this potential, which somehow have on it all the interactions of the system. So we have this physical situation where an incident flux of particles or flux of probability, because now in the quantum context we deal with the probabilities, right? And part of it returns, is reflected, and part is transmitted, right? And this is the situation, and tunneling is one of the most important problems that we deal in this situation. But now we're going to start with something different. We're going to consider what we call bound states. The bound states is a little different problem, right? The bound state is a problem that that is this physical system. So we have this physical system represented by the potential, but the particle is localized itself around this potential. So that creates what we call bound state, right? So we were dealing with the scattering states, and now we are dealing with bound states. And when the particle is bounded, it's very important because that's the energy that the particle can have when submitted to this situation, when submitted to this potential. And normally in this situation, we have to take in account a very important boundary condition. If the system is localized around here, it is not in the infinite anymore, like it was in the scattering. In the scattering, it comes from infinite and goes to infinite. But here now, the wave function must decay as we go far from the system. The wave function must decay to zero because we want to guarantee that the system is localized around the potential. So this is what we call a bound state. You know, we have many examples of bound states, like the electrons in the nuclei, when you make the orbitals, right? When we have a chemical bond where the electrons localize in between the two nucleus of the atoms and so on. So we need to deal with this problem. This is the next problem that quantum mechanics like to deal with, is the bound states. Scattering is one important thing, but now comes the bound state. And we already solved a bound state. And we must, you know, I must emphasize that the wave function is also localized in this case because the wave function square is where the particle actually probabilistically is. Therefore, it must decay when we go far from the physical system, right? So an electron belongs to an atom, and the wave function decays, even though when you go further from the atom, the wave function is decaying. But and there are many situations where we can see how far the wave function goes. When we have those cold atoms colliding together, they start to feel each other when they are very, very much far apart. And that's because the wave function extends around, but goes to zero. It doesn't go, you know, mathematically, you can go to the infinite and then goes to zero, but it decays severely after or beyond the domain of the physical system. Okay, we already solved one problem of bound states, which is a particle in a box. You know, we consider the particle in a box, which is this infinite potential. So the potential is infinite in 0 and in L, and is 0 everywhere, so the particle is confined in this situation. And we solve this by many, many ways, by the Schrödinger equation, which is the master equation, and also by just considering the wave behavior. And we found the energies the system can have. So those are the bound energies. It's not, it's discrete. The energy is quantized, right? So always that we localize, we make this to happen. And we have the wave functions. We determine both of them for the particle in a box, and we got a very nice description of the states with the square is the probability of finding the particle. So the quantization, you have to understand, is consequence of having the wave nature of the particle. And therefore, that if you give a boundary condition, or if you give this potential that holds the particle, you must match the conditions of this wave in the physical system. And therefore, it's not any wave that can exist, only specific configurations of wave or specific frequencies or wavelength, and that quantizes the energy. That's as simple as this, right? And we found this, and I made many explanations about the size, the dependence on the size, the mass of the particle, and always the energy in quantum system will depend on this wonderful constant, which is the Planck constant. But now we want to go to the attractive, because of course to localize the particle we must have an attractive potential, a potential where the particle comes in. And we have many examples. We even gonna give a few examples, and the most important example in nature is the Coulomb potential, right? If you have a charges, like in the nucleus of the atom, it attracts the electron and produce bound states. We're going to resolve the atom in the next few lectures. Therefore, I want to put you a very interesting situation, which is called a singularity. It's called the delta potential attractive. And normally we call this attractive singularity. Is there any application of that? Yes, in many cases, where is missing an ion or an electron in a material, that's like a localized charge center, and that somehow may confine particles. In fact, there is one very interesting application of this, that's the color center. That's giving the color of many minerals around, because you have these color centers that localize, is make electrons going there, and then the energy makes such that the interaction give you the colors we have. So we're going to consider the particles in that situation, and this is a very interesting situation because the potential is a delta function. You may be familiar with the delta function, but in any case, let me remind you that the delta function is a singularity in the space, right? We are zero everywhere except in this point. And what makes sense for a delta function is the integral of the delta function. They must be unitary, right? So it can go to infinite in a very narrow width, in the width going to zero. But what's important is the integral is finite in this delta function. And this is a negative delta function, so the particle is being attracted by this potential. Okay, then we have the potential. You remember we have the wave function. We all know and recall well the Schrödinger equation for this case, right? Minus h bar squared divided by 2m times the second derivative of the wave function plus the potential times the wave function is equal to the energy of the system times the wave function. But here, most part of the space, the particle is free, except in this point. And this is very interesting because it can produce a bound state. And singularity is always important in physics because they always appear. You know, you can have many situations in biomedical in biosystem, and including biomedical situations with membranes and everything that will be very localized type of attractions and things like this that may be well represented by a delta attractive. And this is the most simple atom we can have. Imagine that we have a singularity in space. Could the electron be around And the answer is yes, as I'm going to show to you. So this is like an example of an atom, but a very peculiar atom because it has only one state, as we're going to see. Okay, so you have to understand that this situation, the particle is attracted by this only when it's feeling a big force, only when it's sitting on the zero, on the origin of the coordinates. And of course, we are considering one dimension, but this can be generalized for 3 dimensions as well. So this is an interesting, attractive situation. And for simplicity, we're gonna just, the h bar divided by 2m that appears in the equation, in the Schrödinger equation, we're gonna include in the potential. That simplifies. We don't have to carry many of those constants around. And we're gonna call 2m divided by h bar times the potential. We're gonna call this minus lambda. Lambda is a constant, divided by a times the delta function. You already verified that the delta is like an amplitude and a is like a width, right? And the big question we ask here is if there is a bound state in the system, if actually a particle can hang around this forever, if this can really hold a particle. So let's then consider the equation, solve the equation, and because it's a delta, I have to remind you a few properties of the delta potential, right? And concerning the continuity of the wave function and the continuity of the derivative of the wave function, which is the momentum, right? As we already expert on it. Okay, so let's first consider the Schrödinger equation. And I am already moving things around such that I'm putting the 2m divided by h bar, including the potential, and we call this minus lambda over a times delta. So everything is here. So all the constants of this part of the potential is included everywhere, including here in the energy, right? So that's the equation that we start with them. And I define that way because it's simple, and you're gonna see later why, right? Because this has the right dimension, we put everything in this lambda and a. Okay, now we're gonna call this is a bound state, so supposedly the energy is negative. That's something you should know, that when you have attractive potential of that nature, the bound energy is negative, right? Because it will be zero when the particle is free. Will be positive when the particle is moving around, and will be negative when it's localizing this negative potential. So we consider that eventually we have some energy that here we represent, because this is the energy potential axis, but we also have the energy somewhere here. So we don't know the value of the energy, that's why we're going to determine. And if they exist, right? At this point is not clear. I already told you that exists, but the equations will tell us if it is possible to have a wave around this potential in this nature that stays localized. Okay, then we're going to simplify a little bit. We're gonna move so this energy is negative, so I'm calling 2m divided by h bar square e as minus k square. This is just a notation, just so this part here we call minus k square, right? So we have this, we pass this to this side, pass this to that side. We multiply everything by minus because we want to eliminate this minus. And the equation at the end of this is a very simple equation, because it's nice, because it's proportional to the delta function. And this equation is basically the second derivative of the function minus k square psi equal to this minus lambda over a delta times psi. That's the equation we want to solve. And there are two situations that we have to consider. One is out of the zero, because the delta function only is important at x equal to 0. So x equal to 0 for us, is a very important point. When x is equal to 0, the equation has to be fully considered that way. But when x is different of 0, this term zeroes out because the delta function is not 0, only it's x equal to 0. So that's disappear, that's 0. Right? Okay, so k is positive. So this is a real positive number because we consider the bound state, the energy is negative. And we already deal with this situation. When this is 0, when I remove this term, this is 0. When this is equal to 0, I know the solution. What is the solution of an equation which second derivative minus a constant times the function is equal to 0? It's the exponential. We already saw that. If this was a positive constant, was the oscillatory functions, right? That we call exponential of complex IQX. But here, this is 0, means that the function, the solution of this function is exponential. And then can be a plus and minus exponential. So either because this is square, right? So either a to the kx is a solution, or a to the minus kx is a solution. Therefore, normally, both are solutions. And rigorously speaking, we're going to say that a sum of them is solution for this equation. But we are looking for a bound state. So if we are looking for a bound state, on the negative part of the potential, on this part of the potential, the wave function must go to 0 there. So the wave function must go to 0 in both ends and only be finite in the region of the potential. Therefore, for x less than 0, what we have? If x is less than 0, you know, and the delta is 0 because now we are different of 0, so this term is 0. The solution cannot be e to the minus because when I go to the minus infinite and have a minus in the exponent, this will diverge. So for the x less than 0, which means the negative part of the x, the solution is just the exponential. Right? Because the other term diverges. And we want to localize, which means the solution has to go to 0 when I go very far. And one way, we know that in the negative part of the x is negative. So here I have a overall negative exponent, which decay very fast to 0. Right? So for the first part, if we call this, the first part, 1, and we call this 2, for the first part, 1, we have a solution, which means x less than 0, e to the kx. You know, you can put a normalization, but this is not important this moment. Okay? Now, if x is bigger than 0, we are in the second part of the potential. We are in the second part of the space, which is the x positive. Delta is still 0, so this equation, this disappears. And then I can have a solution again, plus or minus kx here in the exponent. But as x grows, and we are looking for bound state, again, this has to decay to 0 because the probability of finding the particle there must decay to 0 because it is a bound state, it's localized. Particle must be around the potential, the attractive center. Therefore, the solution for this part is the exponential of e to the minus kx, because as x grows, this decays exponentially. So that's a way to have the two functions. So there are two exponentials that decay to 0 as x grow in each side. So it grows in the positive or the negative side. This decays fast. Okay, so this is the two solutions we have, because when we are in 0, you know, this means that this is 1 point, and I just needed to have these two functions matching there. That's why I told you that putting a kind of amplitude in here does not matter, because we're going to require they are equal. So this constant will disappear when we're dealing with the matching conditions on the boundary condition. So the delta function, actually, the singularity in there guarantees an attraction, and we will impose it to the wave function some conditions, but not up to now. Up to now, we just needed to make them to be continuous. Okay, so let's move on and start to work. We know the solutions. Now, around x equal to 0, right, we're going to see how is the matching, because we already matching the condition far from 0, which is the decay of the probabilities, the decay of the wave function. But now, around 0, we must have, as we told you, first of all, the probability, the wave function must be continuous, right? Because we don't have a creation or a consumption of particles in that, so the probability must go continuously. Now, here comes the new concept. The derivative of the wave function must be continuous when you have a finite potential or everything. But in the case of the delta function, it is discontinuous. And we're going to find what is this discontinuity exactly on the point of x equal to 0. So this, of course, is good for x equal to 0. Everywhere else, no. So let's then break down a little bit our lecture to explain to you how is this delta function working here. We're going to start with the wave function. You know the wave function. We're going to start with it. So that's the wave function that we've been considering all the time. So that's good. And now the potential. Let me explain to you in a generic way how is the continuity of the derivative of the wave function in any point that I chose. Here we're gonna go around the origin, x equal to 0. Okay, then I take this, I multiply everything, I pass everything that's not the second derivative to the other side. And then I'm going to integrate, right? This is the second derivative. The integration of the second derivative is the first derivative. We therefore are going to integrate this equation, but we're going to integrate around a specific point. We're going to integrate around 0 here. So we're going to go in a very tiny little region around 0. We call this going from 0 minus, which is a little before, to 0 plus, which is a little after. Okay? That's what we're going to do. Therefore, the integration of the second derivative, we put dx everywhere here you want. We're going to integrate everything, right? So this is everything integrate from 0 minus to 0 plus, which means we're going around the 0 in a narrow space. Now, the integration of the second derivative is the first derivative, right? We all know that. Because the d2 psi dx2 is like dx of d psi dx. dx, so therefore the integration is the opposite of the derivation. And we end by having the derivative on the limit, in the superior limit of the integral, which is the derivative applied to the point 0 plus, which is a little after the potential. And minus, because the integration gives you the value of the function in the superior limit minus the integration on the inferior limit. So we have the derivative in 0 plus minus the derivative in 0 minus. Okay? I hope you all understand that this is what it is here, this derivative. Now, what we're going to do is do the same integration here. So this is 2m divided by h bar times vx cx dx minus 2me divided by h bar integral of 0 plus to 0 minus. 0 minus to 0 plus, sorry. But this function is continuous And 0 minus and 0 plus are very close to each other. Right, this is 0 minus. Therefore, since they are very small, this integral is integral in an infinitesimal range. So this gives you 0. This goes away. So the discontinuity of the equation, this is because the wave function is continuous, right? So therefore, it minus in the wave function a little bit before and a little after the 0 must be equal. And that gives you 0 in this integral. Now, we have this part here. If the potential is a smooth function with no big discontinuity or anything, this will be also 0 because we are integrating a function from a narrow limit around 0. So this is also giving 0. But when this is a delta function, this is not true, because when this is a delta function, the integral is only valid at 0. So that's give you the value of the function if the potential is a delta function. So if the potential is finite, the derivative is always continuous, and that's what we've been using. But when the potential is a delta function, we know that the delta function is the only value is the integral at 0, and give you the value of the function at 0. So if the potential is the delta function, or is a alpha times a delta function, like this, the derivative of the wave function give you 2m divided by h bar, which is this term, times the value of the function. You know, of course, the constant that comes in front of the potential stays here, but times the value of the function at 0. So, because this is not 0, it means that the derivative is discontinuous at this point, when we have a delta function. So, only and only when you have a delta function here, the derivative is 0. So, the derivative has this property of really changing the momentum, because the slope of the wave function at that point will not be the same in each side of that point. So we then learned this, that the derivative of the delta function must not be 0, right? The derivative of the wave function, the continuity of the derivative of the wave function around 0, in this case, is not 0, but depending on the value of the wave function at the 0 itself, right? If it is big there, then the discontinuity is big. If it is small, it's small. Okay, so applying this relation, we know that 2m divided by h bar square times the potential is minus lambda over a. So the derivative of the wave function has a discontinuity, which is minus lambda over a times psi in the point 0. Now, we know what are the functions, and we know how to take the derivative, and we know how to take the derivative in the point 0, which is the point where we have the singularity, we have the attractive center. Okay, well, because the wave function is e to the plus minus kx, depending where you are, in what side of the x, positive or negative you are, we can take the derivative, and the derivative of the exponential, you just get the k here. The minus k in one side and plus k in the other side, but we have the minus here, so we get the minus again. And it applied to 0, it's get 1, because exponential of 0 is 1. So I have the derivative as minus k here and k here, but they are, of course, one minus the other, and that gives me minus 2k. So minus 2k is equal to minus lambda over a times the wave function at the 0, 2. But the wave function at the 0, because I already explained to you before, it is 1. We chose the 1 here. We chose the coefficient to be 1. We could normalize the wave function if you were interested in normalizing this wave function after all. Okay, so the wave function is also 1. So it turns out that minus 2k is minus lambda divided by A. As you know, lambda and A are the characterization of this delta attractive potential. So as result of this condition, we get k equal to lambda divided by 2A. But we know that k squared is equal to minus the modulus of the energy, and we know the energy. We know that the energy is negative. And this has to be this term square. So it's lambda divided by 2A squared. At the end, we can extract from here. Right? We can extract from here. Oh, I apologize. This is I don't have the minus here, because the minus will be in the modulus of the E. Okay, so we have that E equal to, from here, I extract the energy, so I get lambda squared divided by 4A squared, right? But then I have a 2 here, so I have 8m and lambda squared. So I end by finding the energy of this bound state. That means that I have energy. The particle that will be bound to this attractive center has a specific energy. Cannot have another energy. That's the only possible energy of this attractive center. So particles that are bounded in this attractive center will have specifically this energy. And this is a very interesting. There is only a single energy. We don't have two possible bound states. We don't have a sequence of quantum states for this specific attractive potential. We have only one. And that's given by this. So it grows with the potential, of course, depending on the parameters of the potential, it grows. And you see, it has this formulation. Now, there is a exercise I want you to do, because we have done attractive potential like a box, right? So I want you now to make a box that the width goes to 0 and the height goes to infinite. A finite size box. And I want to see if you recover this, because if I have a square well potential, right? If I have a square well potential like this, right? And I make this width goes to 0, and I make this height goes to infinite, we're going to get a delta function. So we must reproduce, and then only one state, one attractive state, one bound state should be allowed in this potential. So you can do this exercise yourself. But what we have for the wave function is something like this, right? The wave function grows such that the localization of the particle is very, very much concentrated at the proximity of the attractive potential. And that has this tail that goes to infinite, right? And which means that even though the particle is attractive, the particle is bounded here, it has the chance to visit, you know, distances, to visit far away. And that's very interesting, because sometimes you come with two attractive potential close by, and then the particle can be divided between these two. It's a very interesting and very rich problem. But, you know, what is important is that this singularity, if you have an attractive singularity in some materials or in the biological system, it will produce a specific energy. And then you may have many applications like defects. You know, suppose you have some solids where you remove an ion or remove an electron, so you create a specifically localized potential. And then if you have a solid and you remove one electron, then of course that side became positive and can attract another electron to be bound to it. So you can somehow make analogy with this. And of course, we have to know that the energy will depend on this ratio of amplitude of the potential and width, as we know. And of course, I ask you to consider in your homework just a potential like this, a square potential. Solve the potential for a bound state. You have some energy. And of course, if this is a square well potential, attractive, you're going to have many bound states. But as you decrease the width and increase the height, right, the depth of the potential, you can recover the energy of a single bound state, which is interesting, this, because depending on how many bound states you have, depending on the energy, you're going to have different characteristics of this physical system. Okay, so this was an interesting problem, and of course we can have more applications of it. We don't need to stop in just saying that this is a singularity. So I list here some possible applications that we may visualize, like interface between two metals. When we have two metals, this is a very important kind of situation. I have one metal, and I have electrons that are free here. And then I have another metal very near this metal in an atomic type of spacing. And then in between, what we can have is an oxide. So normally we can have here an oxide. So if we have an oxide here in between the two metals, right? So what we have here in this example, let me explain to you. This is an oxide, this is metal, and this is metal. And they can be the same metal or different metal. What's interesting is that the electron is free in the metal, as we know, is a good conductor. Well, the electron is free here, like in the delta potential. But here, the electron is not really free. And this interface may have ways of attracting this electron. And this is like a 1D model. So we have like a one-dimensional model. And the electron may be bound to this. So we may get a bound state here and make the electron to localize more around this layer. And of course, it has to be like a material that has levels like a scepter of electrons, so it's attractive to the electrons. And we can create equivalent. And this is a very important type of junction in electronics, in many applications we have, and even in some biological situations where you may have something between transmitters that will localize the electron. So that's a delta function in this case will be great. And it is also a one-dimensional model for an atom. Suppose we don't know anything about atom, which we're going to learn in the next lecture, in fact, or in the next few lectures. We can say, well, an atom is this attractive singularity caused by the nucleus and the electrons hang around. Of course, we could never explain some of the things if we do this one-dimensional model. We could never explain the transition lines and everything, but it's a model anyway to show that the quantum mechanics produce this kind of effect. Okay, and this can also be a model for electrons or ions in membranes or interfaces, where the dimension is very tiny. The potential is limited to a very narrow region, and it can somehow show interesting effects, because the electron will be bound there. Will be, you can have the wave function spread a little bit without flux. It's a real wave function, remember? But it is localized, a bound state, and you can have many consequences of this. In some situations, you can produce a charged layer, right? Because you can attract in this singularity many electrons, and they be bounded there, and then you produce a very interesting kind of configuration. And sometimes you produce even a 2D in the interface. It's a 1D perpendicular to the interface, but in the interface, you produce a kind of 2D plasma or conductor or anything. Okay, so this was a great example. And now we're going to do another example, but we're going to do in the next lecture, which is the second part of this lecture. Bye-bye.